Hello, I'm pleased to be here once again in Unit 2 NUC headquarters in order to deliver a new course in mathematics for student reading in economics. Now this course, which is entitled Calculus, actually it's a prerequisite for all courses and all topics again for the students he has to study, whether in mathematics, physics, engineering, and even in economics, because you have cyclic behavior in the market, you have a change in the demand, and this is why you have to resort to calculus. Now, this lecture is an introductory one in order to show you how calculus developed through the ages. And as a science, it addresses two main problems. Now, the first one is called differentiation. And differentiation means that to be able to calculate the slope of the tangent at any point P on the graph y is equal to f of x. Now, the slope of the tangent here is the terminology that engineers, as a matter of fact, use. Whereas physicists, they call it the rate of change, like the rate of change of velocity, for example, with respect to time, which is the acceleration. Mathematicians use the word derivative. As to economists, they have a different vocabulary. They use, for example, instead of the rate of change, the marginal change. Like they say the marginal change, the marginal cost of production, or the marginal propensity to consume, which is the change in consumption divided by the change in income, for example. And they may also use, for example, the word elasticity. Like, for example, they say the elasticity of demand, which is the percentage change in the quantity demanded divided by the percentage change in the price. And it reflects the consumer response to the change in the price, i.e. How the price or the change of the price affects the demand, etc. And of course, here, for example, when it comes to the elasticity of demand, it's usually negative, because the higher the price, the lower the demand. Now, this problem was usually dealt with in the ancient eras by taking two nearby points to the point P and then connect them by a straight line, and then calculate the angle by which this straight line makes with the x-axis and then get the tangent. But to calculate it exactly, now we have to resort to a concept in calculus called limits. Now this is the first problem. Now the second problem is called integration. And integration, as a matter of fact, is, you can say, the opposite problem to differentiation. Integration is to be able to calculate the area A under the graph y is equal to f of x in the closed interval a, b. And what they used to do in the ancient eras is that they divide the base AB into equal subintervals, and then they construct perpendicular to this base, and to cut or to meet the graph to obtain a set of trapezoid, and to sum up the area of these trapezoids, they get the whole area. But again, to calculate it precisely, you have to resort again to the concept of limits. Now, the concept of limits, the meaning of the limit, as a matter of fact, is to be able to, if you have an unknown quantity you wish to calculate, what you do in principle is that you let it approach to other quantity easily to be calculated. And the more you control the difference between the two, and you let the unknown quantity approach the other one that you can calculate, then you would be able to calculate the unknown one. So let us read it as it is from its definition. Now, this is a verbal definition of the limit. It separates, first of all, this is the beginning of calculus, because before that, you, of course, use many pre-calculus topics, such as algebra, etc., functions, but when you start with limits, it means that you start with calculus. So it separates calculus from algebra, and it seeks to determine an unknown quantity by letting it approach an easily calculated one, such that the difference is within a controllable accuracy. Now, the more they approach each other, the more it becomes possible to calculate the unknown one. Now, let us see how this works. Now, to give you an example, now this is an animated applet designed at Cairo University in order to show you how the limit works. And actually, the subject of limit, or the idea, the concept as a concept of limit, it has been known, or historians say that it has been known from the ancient, very ancient eras. For example, the ancient Egyptians, the Sumerians, the Babylonians, they knew it, but not precisely as like the mathematicians have introduced it in the late 18th century. Now, this is a circle, and they wish to calculate the area of the circle. So what they do, in fact, is that they subdivide the circle into 4, for example, equal circular sectors. And then they organize them such that the base, because you get almost 4 equal triangles. Of course, they are not triangles, but you organize them such that the base of one coincides with the vertex of the other, so that they almost become equal to a rectangular. Of course, here you have half the circumference, which is pi r. Of course, pi itself is another story. To calculate pi through the edges, it's another story. But if you almost have an approximate value or a crude value of pi, what you do is that the base becomes equal to pi r, whereas the height of the rectangle becomes equal to the radius, which is r, and the area of the rectangle is equal to the product of the two, which is pi r squared. Now here, of course, the 4 sectors do not coincide exactly with the rectangle, but the more you increase the number of subdivisions, and the more you get to approach the rectangle, and the more you do them, the more again you approach more and more. So what you do exactly is that you have the unknown quantity, which is the circle, and the known one, which is the rectangle. And the more you let the circle approach in area to the rectangle, and you know the area of the rectangle because it's easy and this is known, so then you can create the area of the circle. Here is when you have, for example, 32 subdivisions. So when you run the solution, here it is. What you get, in fact, is almost a rectangle. So since the base is pi r and the height is r, so the area of the circle becomes equal to pi r squared. Now, if you this is it. This is again the same problem on the slide. This is the base pi r, and this is the height r, and this is the circle you wish to calculate the area. It becomes equal to pi r times r, which is pi r squared. Now, there was a mathematician, a very known, one of the 4 renowned mathematicians in the history of mankind, called Archimedes. He set himself in 300 BC to calculate the square of the parabola, and he did actually the same thing. He used a concept in mathematics called the exhaustion principle. As a matter of fact, it's not his, it's of another previous mathematician, but he said to calculate the area here inside the parabola. Now, parabola, what's the meaning of a parabola? Parabola, it's a kind of conic sections. You have a right circular cone, and you cut it by a plane. If the plane is perpendicular to the base, you got a hyperbola. Inclined to the base, you get an ellipse, and parallel to the directrix, you get a parabola. And he wants to calculate the area here enclosed by the straight line AB. So what he does is that he obtains the farthest point P to AB, to the straight line AB, and then on the straight line PB and PA, he constructs 2 other triangles. Now, the first approximation to the area here, the enclosed area here, is the triangle, the area of the triangle PAB, whereas when you construct another 2 triangles, he can show that the area of both triangles is equal to 1/4 of the first one. So now the area here becomes equal to the area of PAB 1 plus 1/4. And each time he constructs a new set of triangles, the sum of the new one are equal to 1/4 the previous one, so you get here 1/4 square, etc. And he knows well that the sum of this is called a geometric series, the sum of which approaches 4/3. So the area inside the parabola becomes equal to 4/3 the area of the first triangle PAB. And this is actually the first ever result in calculus, and it is a result in integration and not in differentiation. So as a matter of fact, it's integration that was discovered first, and then differentiation. It was only thanks to Newton that we teach nowadays differentiation, then integration, because Newton discovered with Leibniz, a German mathematician, in fact he was a diplomat, interested in mathematics, they discovered what's called the fundamental theorem. They didn't discover calculus. They discovered the fundamental theorem by which, instead of summing up areas with trapezoids, etc., they can use what's called the antiderivative of a function, and therefore you have to teach derivative first, and this is why differentiation precedes integration when we teach them to students. But in history, it was integration that was discovered first, and then differentiation. Now, if we apply this result to this to this square here, what you get here, you apply, you know that the area inside the above the graph, you take a graph y is equal to x squared, so the area above the graph is equal to 4/3 the area of this triangle, but this triangle has an area of 1/2, then the area above the graph is 2/3, and since the area of the square is 1, because it has a side length 1, so the area beneath the graph is equal to 1/3, and here you get it in this form in our new symbols. The integral from 0 to 1 x squared dx is equal to 1/3, and this in fact is the first result ever discovered in calculus in the ancient times. And now we have to wait another, in fact, 20th century until a French lawyer came of the name of Fermat, and he said that we calculate differentiation. Now differentiation comes. We have to calculate differentiation through calculating almost this quotient here. You have, for example, let's suppose you have, for example, so here we have, for example, what he does. This French lawyer, he took, for example, y is equal to bx minus x squared. This is again a parabola open from below, and he wishes, for example, to calculate the slope of the tangent at any point here, x naught, for example. So what he does, he uses the formula f of x plus h minus f of x divided by h. Here it becomes equal to b of x plus h, of x naught plus h minus x naught plus h square, minus bx naught plus x naught squared divided by h. Here, when you subtract equal terms, what you get here, b minus twice x naught plus, for example, or minus here minus h. This is what you, in fact you get, and for example, you cancel or discard h, and this is actually the tangent of your straight line here, which is the tangent of this angle here, is called the slope of the tangent at this particular point, x naught. It's equal to b minus twice x naught. Now, so suppose he wants to calculate, for example, the maximum of the function. So what he said is that it's the point at which there is no much change in y and there is a little bit change in x. So what he does, he subtracted f of x plus h minus f of x, and he set that to 0, and he substituted in his expression here, and then he discarded h and h square, and he arrived at this point here, x is equal to b over 2. In fact, this is one way of doing it, but there is another way of doing it, is that you can, here the same graph, is that you can, attribute an equation or assign an equation to this straight line, the equation of which at any point x naught is equal to what? Is equal to y naught, which is equal to bx naught, again, minus x naught square, y naught, plus m, which is the slope of the line, which is unknown now, times x minus x naught. This is the slope of the line. And if you solve this with the equation of the parabola, which is again is equal to b minus bx minus x square, what you get an equation, second degree equation in m and in x. So you set the discriminant to 0 because you have here only 1 point, because since it's a tangent, so it touches at 1 point, not 2 points. You set it to 0, and the unknown, which is m, you can obtain it as bx naught again, as b minus twice x naught. So this is another way of doing it. And actually, this method was proposed by a philosopher called Descartes. He's the one responsible of transforming Euclid geometry into algebra in what is called analytical geometry. And this is the method he proposes. And now we had two methods of approaching the subject or of calculating derivatives. But then the second method, which is this method, sometimes it works and better than the first one. The first one, you have h, you have to discard h, etc. So actually, for example, he give this curve, which is called folium of Descartes, and this curve here, in order to approach it or to calculate the derivative using the method of the first mathematician, it was difficult, and this is why the first method has to stop for some time until what we call them the big guns, Newton and Leibniz, came into being, and they could use the method. Here is Newton. He used his method called fluxion by inserting a small parameter or variation called the fluent, and he, instead of introducing a small increment h to the function, to x into the right hand side, he introduced a small variation both in x and in y. That in x is called x dot o, and in y, y dot o. And after manipulating and discarding o and o squared, he arrived at this simple expression which gives you the derivative or the relation between x dot, meaning derivative with respect to time, and y dot of this expression here. Now the same thing was done by a German mathematician. This German is called Leibniz again. In order, for example, to calculate the derivative of x cubed, what he does, he takes, for example, y is equal to x cubed, so y dy is equal to x plus dx cubed. And when you expand this, you get x cubed plus 3x squared dx plus 3x dx squared plus dx cubed. So dy becomes equal to, in this thing, x by subtracted from this x cubed. So you got 3x squared dx plus 3x dx squared plus dx cubed. And then here, if you want to divide by dx to obtain the derivative, you got dy by dx is equal to 3x squared plus 3x dx plus dx cubed squared. Now here, again, the same problem appears. Why? Because here, as you see in the slide, you have here dy by dx is equal to this. So what you did actually is you divided by dx. And once you divide by dx, it means that dx is not equal to 0 or can't equal to 0. And at the same time, in order to obtain the derivative, it becomes equal to 3x squared, which is the derivative of x cubed. And then you have to discard dx here. So on the right-hand side, you set dx equal to 0. And at the same time, you divide by dx. So dx is 0 and it's not 0 at the same time. And this is why the method has something wrong, of course. It's not wrong because limit was not introduced yet. And this is why the philosophers called their method, whether Leibniz or Newton, ghosts. In fact, they meant Newton at the time, ghost of departed quantities, because these are ghosts, the x, because at the same time they appeared because you divide by them, and they disappeared on the right hand side. But their method is completely right. So now we come to what's actually the terminology of both, whether Newton and Leibniz, what we do for differentiation. Now, for differentiation, we use a lot of symbols. There is no one unique symbol. You can use y dash and f dash of x. These are symbols, notations used by a French mathematician called Lagrange, and these are the notations of Newton, meaning differentiation with respect to time. Whereas here, this is the same symbol, denoting the same symbol or the same meaning, which is differentiation with respect to x by a person called Bernoulli. In fact, there are 12 of the Bernoullis. They are Swiss mathematicians and physicists, and here are the last two, which are the notations of Leibniz. So in fact, Leibniz, what we say when we say calculus, we mean the calculus of Leibniz, because Leibniz, in fact, whereas here, or Newton, although they did some advances in calculus, but the main, in my opinion, in my view of Leibniz, is that he introduced his eternal, immortal symbols called dy by dx and df of x by dx. And in fact, I recommend that the students use these symbols because they're easy to work with, and these are the symbols of Leibniz, as I said, and they succeeded in transforming calculus into algebra. And this is why the subject is not called differentiation, but it's called calculus differentialis integralis, means the calculus, the calculation of differentiation and integration. And to see how this works easily, for example, you have y is equal to sine square root of x. Now, to see how calculus works, now you have, this is a composite function because you have a function logarithm, you have a sine, you have a square root of x, and you want to differentiate y with respect to x. So what you do, you set square root of x equal to v, and the sine v becomes equal to u, and then the whole thing inside the ln is equal to y. So you have here y is function of u, ln u, where u is equal to sine v, where v is equal to square root of x. So if you want to set to obtain dy by dx, it becomes equal to dy by du times u by dv times dv by dx. So you have here some fake or dummy variables called u and v, and if you can cancel du with du and dv by dv to get dy by dx. But then if you want to calculate dy by dx is equal to directly the derivative of u, of ln u, times the derivative of sine v times the derivative of square root of x, and all of them are elementary functions easily to be calculated. Same thing here. If you have what we call parametric equations, you have x instead of y function of x, you have an x function of t and y function of t, and of course you can obtain by deleting t between x and y, you can obtain y as a function of x. But this kind of representation is more viable, more suitable to applications like kinematics, for example, in physics. So again, if you want dy by dx, it becomes equal to dy by dt derived by dx by t, because you can cancel from both the numerator and denominator t. So dy by dt from here is equal directly to cosine t divided by derivative here minus sine t, and you get directly minus cosine t. So again, you see the ease of using Leibniz notations. Again, when you have y of x, you get the differential d of y of x. You have here y dx plus x dy, and you can divide by dx. So here you cancel dx, here you get y, and you divide by dx, here you get x dy by dx. Or you may obtain dy of x by dt. Then you divide the right hand side here by t to get y dx by dt plus x dy by dt. Or you can again calculate d to y by dx, d to y of x by dx square. After you calculate d of y of x, you multiply by d, so you get d of dy of x. Here, again, you imply the differentiation or the differential of this expression here to get this, and then you divide d to y of x by dx squared to obtain the second derivative of y of x with respect to x. You divide here by dx squared, so here becomes dy by dx. This becomes y d to x by dx squared, and this again dy by dx, and this x d to y by dx squared. But this is again equal to 0 because x, the derivative is equal to 1, second derivative equal to 0, and you get at the end twice d to y by dx plus x d to y by dx squared. Now, nobody actually uses the differential to obtain the derivative of y of x, but just to show you that how strong and efficient the notations of Leibniz. So when we say calculus, we mean the calculus of Leibniz. Actually, Leibniz introduced also the notation, this notation here meaning integration. And this symbol here is the first letter in the Latin word summa or sum or somme in French. You use it to denote integration. And also it was him who introduced the concept of integration, of function. The word function also is credited to Leibniz. Now here again, how to use the notation of Leibniz to carry on integration. If you have a function like this, you wish to integrate it, all you have to do is to set e to the x equal to a new variable u, to obtain using his differential e to the x dx is equal to du, and you transform this integral into a small or a much simpler integral, easy to calculate. Now again, going back to integration. Now the subject of integration here, how did we do it in the first beginning? You sum up rectangles like this, and you carry the summation, and you get the whole area. But of course, this is difficult, and you have to do this. You have to resort to series. For example, if you have a straight line, then the series which, because you sum up the height times the width. The width is, for example, 1 or delta x, and the height is equal to the function, the value of the function at this particular value of x, and then you add up, you keep adding up the height of the rectangles, so you have to use a series of this sort. This is an arithmetic series, and it's easy to be calculated. The second one is again, it's not an arithmetic series, but a series that was known in the ancient times. If you and it's used when you use, for example, you have the function is a parabola. But when you increase the order of your function, you need more. If you need to calculate or to sum up areas by this way of adding up rectangles, then you would need some of more complicated and cumbersome series. These are, again, as a matter of fact, finite series. But then mathematicians in the ancient eras, especially the Greek, for example, they thought that these series are difficult. You remember, for example, the paradox of the tortoise and the racer, and how the tortoise, for example, was ahead always of the racer, yet the racer or the runner, his speed was 10 times the tortoise. Again, you have Zeno paradox, for example. How come, for example, you are aiming your arrow at an object? How come it traverses an infinite number of points and yet it reaches the object? These kind of infinite series were devilish in nature. They didn't like to approach them because you get always contradiction. But then, by the advent of calculus, you have series like, for example, this one, the geometric series. But you have to approach it through what is called convergence concept. This one, for example, you cannot sum it up 1 plus x squared, etc., to infinity, unless the model of x is less than 1. For example, this is a sequence which is called it monotonic increasing, because it goes up all the time until it ends up, for example, here with, this is called the limit of the sequence. The sequence, it goes up, and then it's bounded above. Why it's bounded above? It's bounded above by 1 here. So it's monotonically increasing and bounded above. Why bounded above? Because n is less always than n plus 1. So it ends up with what's called a limit. And the meaning of the limit, we shall demonstrate this in a later lesson, is the value at which, if you have any neighborhood to this limit, you always contains an infinite number of elements of this set or of this sequence. Again, this is, they succeeded in the 18th century of addressing the subject of limits again by getting or extracting or deducing some constant. Like, for example, this one here is called Euler constant. This one is Euler number. We shall be seeing this when we deal with phenomena of growth and decline or decay. Here, the Euler constant is the difference in the sum of the green areas, and whereas E, for example, is the sum of this series, which is convergent all the time here. Now, we saw now how series could be summed up. But then two mathematicians in the era of Newton, they were able to sum up, to transform functions also into series. This is called a Taylor expansion of a function. We shall see this in detail, how you transform. And this is how, as a matter of fact, your calculator works. Your calculator, when it works, you have various buttons, and you wish to calculate x squared, square root of x. But when it comes to series, to functions which are not algebraic functions, like the sine, the logarithm, the exponential, you have to transform your series and your function into a form amenable to algebraic manipulations. And this is the way of doing it. This is called a Taylor expansion of a function, and this is the error which you end with when you approximate your function with a series. Now, mathematicians, they started to think at that time that you need more rigor, as a matter of fact. You need more rigor because at these ancient times, all these concepts were, I would say, are of a crude way or a crude understanding of these concepts, and you need to be more rigorous. So there were two mathematicians, a French and a Czech, at the late 18th century. They started to question the old concepts, like, for example, continuity. Of course, continuity in our language, it just means that something goes on with time continuously. Like you draw, for example, a graph, it continues indefinitely. But it's not the case. Mathematicians have to be more rigorous. So they designed continuity, said that there's difference between the value of the function and the value at a nearby point x plus delta, and if you can make the difference smaller than any required or prescribed quantity epsilon, then in which case you can say that the limit of f of x as delta tends to 0 is equal to f of x, and that's the concept of continuity. And you need continuity if you want to differentiate a function. Again, you can describe, knowing now the limit, you can describe the derivative of a function by this expression here. This is the one that we're going to use. This is how since Leibniz introduced or said that dy by dx is equal to f of dash of x. So this French mathematician, he said, why not then introduce the first differential coefficient, saying that dy is equal to f dash of x dx, and instead of calculating the exact change in the variable y, which is the dependent variable, why don't we move for example, in the direction of the derivative. So it's like driving a car. So instead of turning with the road, what you do, you leave the road at an instant point of time. So instead of having the change in y, you have a d of y. And the d of y, you can actually use this approximation to get, for example, square root of and values of function that are difficult to calculate using a first approximation of differentials. Now we come to this is the main breakthrough actually in calculus. Calculus was known since, as I said, the 300 BC, but the main advent of the fundamental theorem of Newton, he said that if you can differentiate the area to obtain the function. In other words, if you have here the area as a function of x and the area at another point x plus h, so the difference divided by h, you get f of x. Here f of x is a continuous function of x, and a is a differentiable function of x. So what you say here, the derivative of the area is equal to the function. In other words, that the area, since you differentiate it, you get f, it's an antiderivative. So it's an antiderivative, and at the same time it's an integral. So now we can state that antiderivatives are integral. Why? Because they are not so exactly. But when the function is continuous or having an antiderivative, what the derivative of the integral becomes equal to the function, and this is called the first fundamental theorem, and from which you can get the second fundamental theorem. So we read the slide then. F can be integrable, yet not necessarily continuous or having an antiderivative, because actually integration now and differentiation are not opposite to each other, according to Riemann. And this led Riemann to use what is called the Riemann sum in order to evaluate the integral. In other words, the function, if it is continuous, then it's integrable, but if it is not continuous, then doesn't mean that it doesn't have an antiderivative, because continuity is a sufficient condition for having an antiderivative, but it's not necessary. Functions may not be continuous and still having an antiderivative. But here you've used the fundamental theorem to calculate the integral. But suppose that the function is not continuous and has no antiderivative, but is integrable in the sense of Riemann. Then what you do, you get the Riemann sum, and then you get the limit of the Riemann sum, and from this you set up the integral. In fact, mathematicians started to question rigor in mathematics, not only continuity, but it was thought, for example, that functions of this sort, for example, you have modulus x here. This has here the derivative, because this is 45, the derivative is 1, and this is equal to minus 1, whereas the function has no derivative at x equal 0. Now, function of this sort, mathematicians thought that functions may be differentiable everywhere, except at some particular points, until this mathematician called Weierstrass at the late 19th century, he came up with a function which is very odd. This function here is called, it's a uniformly convergent. Actually, uniform convergence is a concept use of series of functions. Here you have 1 over twice to the power n. This is a geometric series times cosine to the 3nx. Now this is bounded by 1. We know that cosine bounded by 1. So actually 1 over 2n, this is a convergence series. But not only that, because you have here cosine 3 to the x. So the coefficients are convergent, but the series itself is also uniformly convergent according to a certain test. So this implies that you can differentiate it, integrate it, and at the same time, it's continuous. So this function is continuous for all values of x. But because actually here 1 over twice to the n, the ratio is half, which is less than 1. So when you differentiate it, you get 3 to the power n outside here, so you get a ratio which is greater than 1. So the derivative here does not exist, which means that this function is continuous for all values of x and differentiable for nowhere. So it's continuous everywhere and differentiable nowhere. So things of this sort become when mathematicians become to think more rigorously about calculus, they try to establish, in fact, calculus on a strong basis. So this same mathematician introduced this limit mechanism. Of course, finding a limit is something, and proving the existence of a limit is also something else. Now, the limit mechanism suppose that if you want to prove that a function has a limit at a point A, because the function may not be defined at A, but it has a limit, all you have to do is that you introduce two pair of numbers delta and epsilon, such that when x in a deleted neighborhood of the point A, the function can be in a deleted neighborhood of a value L. In other words, if this inequality is true, then this leads to that. This means that the limit exists. So now calculus now started to be based on more rigorous concepts. In the ancient eras, we saw that mathematicians, they understood very well the subject of calculus and the subject of limits too. For example, Newton knew what's the meaning of limit, except that he didn't use these rigorous mechanism of the late mathematicians. So the mechanism itself was not known, but the idea itself, of course, was known. For example, we have seen how the ancient people, for example, used to, historians, of course, there are no written things meaning that they knew the way of calculating the area of a circle, but they knew the area of a circle. It's very well known. So historians thought that that was the way. And actually, a mathematician, Archimedes himself, the way we saw the way how he calculated the area of a parabola. For example, here is the parabola that Archimedes wants to calculate the area. So what he did is that he took any 2 points A and B, and then this is how he did it. He approximated the area of the parabola into the first triangle, and then he built up the second 2 triangles, and so on. And therefore, the area of the parabola becomes equal to the sum of these area of triangles, which we saw that is equal to 4/3 in the limit of the area of this first triangle. So the limit himself, the concept of limit, actually was there. So now we come to the end of the subject of calculus, and we have, as a matter of fact, exposed you to the evolution of how calculus developed. From the very ancient times, it took about 2,000 years to establish on a rigorous basis, and it's actually a subject that all the students must know it, must study it, because from the very beginning of your study at the university, you always encounter phenomena that is subject to change, and actually calculus is the subject that you have to study. And here we exposed to you the subject from the very ancient time from Archimedes. This is the first mathematician that was thought to have introduced or discovered the idea of limit of, it's called the squaring of the parabola, until we end up with Weierstrass. And with that, actually, we have come up to the end of this first introductory lesson. And then we shall take all this concept one by one next time, not only the subject of limit, but the functions, all these terminologies and all these concepts that we expose in this lecture, we shall do them in great detail. So until we meet next time, of course, all these lessons are uploaded to the site of the university of Unit 2. And until we meet again, I'm wishing you very good luck in your study. And thanks for your attention. And until we meet, thank you very much.